Today, I will give an overview of chemical recycling, and myself, I am Anna Edsberger. I'm a researcher at RISE Research Institutes of Sweden, focusing on chemical recycling of mainly textiles. I'm joined by two gentlemen who are also very well virtued in this world. So it's Anders Arkell, who's the technology officer of Rewin, Swedish company doing fiber-to-fiber recycling of polyester, and Megan Nathan, head of functional surfaces and style at Autoneum, who will tell us a bit more about how did they transfer from having a very mixed input on some of their components into making components out of polyester-based materials. So I'm really looking forward to spending this lunch hour with you. So just to get everyone on board with where do we place chemical recycling in this map. So of course, the most efficient thing, as always, is to reuse materials. If that's not possible, remake is the next best option. After that, we start going into the different recycling opportunities. So we have mechanical recycling, where we open up a fabric and we reveal the individual fibers, and then we have to come back and make new yarns. The next step is that we do thermomechanical recycling, or we use solvent-based methods. Then we're going back another step in the buildup of a fiber. So then we release on the polymer level. So either we do that by dissolving in a solvent or by melting the material. And then we need to go back and do a fiber spinning process. If we go then even further back in this chain, we will be doing polymerization. So we first do solvolysis, where we break apart the polymer chains. We release the monomers. They are depicted down here, so small molecules. And then we need to do a polymerization to then be able to do fiber spinning. And if we go the full road back, using pyrolysis or gasification, we will release gases, small molecules. It's equivalent of what you would do by cracking an oil, which means that you would have a lot of steps coming back to a garment. So what you see here on the top is that the energy demand is increasing to the left. So we use higher energy, we use higher temperatures, we use more energy in order to actually perform the processes. And we also need more energy since we've gone further back into the construction of a textile. We also need to take more steps to come back to a textile again. And today we are going to focus on this step called solvolysis or chemical recycling. At RISE, so about 3 years ago, our research in chemical recycling was almost exclusively done based on the funding from research grants. And we used some 10, 12 years building up knowledge in the area. And today, about half our revenue on this matter is actually from the private sector. So we are very happy that we've been able to do this transition together then with partners and with companies that are now utilizing the knowledge that we have built. And as a research institute, this is really how you hope that it should work, that you start out with gathering a lot of knowledge, and then at the end, you can actually, that can be utilized in real life, real world processes. Just setting the scene a little bit and also putting this into perspective. So today we're going to talk about chemical recycling. When it comes to the life cycle footprint of a garment, of course, there are many different processes that has effect on that. So you have a product, it becomes waste, it's collected and sorted. You probably have some kind of pre-treatment like decoloring. You make a fiber production, you manufacture a new product. And if we look on this from a life cycles perspective, so this is a study from Mr. Future Fashion, so it's starting to become a little bit old. I think it's from 2017. But what we can see here is the life cycle, or sorry, the carbon footprint of a garment, and this is a typical Swedish garment. In Sweden and the Nordic countries, we're big fans of cotton. So that means that the fiber production slice here, the blue slice, is rather small, and not a lot of CO2 is released by growing cotton, but instead you use a lot of water, for example. This slice that's then related to fiber production can be up to 40% of the cycle if you have synthetic fibers such as polyester. Then we have a large part of the cycle that's related to manufacturing of a garment. And here we see that, for example, the wet processing is a large share of this. So what I want to highlight here is that what we're targeting here, which is related to fiber production, is a very important step on the road. But as a textile producer, there are many different ways you can use in order to reduce the CO2 footprint of your materials. And my main message here is let's not be discouraged by maybe the road you have chosen is only a small part of the circle, but we have to work on all of these different parts of the circle and work from many angles simultaneously. So, just a little overview today, some recycling actors. When it comes to polyester recycling, we have three main technologies. So starting with PET, polyethylene terephthalate, we can use enzymatic breakdown of the polyester. It will form the monomer TPA, looking like this. If you're a chemist, this makes you happy. If you're not a chemist, it makes you scared to see these molecular structures. You can use methanolysis, which means that you're breaking down the PET molecular chain by the use of methanol. Your end product there will be something called DMT. It's a different variation of the building block of polyester. You can also use glycolysis. That means you're breaking the polymer down in ethylene glycol or another type of glycol. Your end product then would be BHET, monomer looking like this. And then one of your last options is the hydrolysis, which means breakdown in water, typically aided by either an acid or an alkaline environment. You will have then a TPA looking like this. And then there are some other processes like aminolysis and monolysis, but these are mainly used at an academic level. But the methanolysis, the glycolysis, the hydrolysis, and the enzymatic methods are currently used either at the startup state or industrialized. So here you can see some of the actors. You can see that currently the glycolysis is the most used method. It's a rather, from an industrial point of view, rather easy method. You typically don't need to go to high pressures. It's a well-studied process, so it has a lot of benefits, which has made a lot of companies go for this solution. You have a smaller share here of companies going for methanolysis. In here can be a bit more of a challenging process because typically you will need to go to highly pressurized systems. Actually, this actor, Recyclit, has developed a method of low temperature methanolysis. I spoke to them this summer and I asked them what their secret is. Of course, they couldn't tell me, but I would guess it's in the catalyst. Enzymatic actors, not very many. We have Carbios, we have Samsara, then using enzymes for the degradation. And then hydrolysis, we have also some actors. Hydrolysis is also quite versatile. You get high yields. The difficulty is that you typically need to use a lot of auxiliary chemicals. So you would do this, I would say, almost always industrially in an alkaline environment. And in order to get your product, you need to use a lot of acid in order to to precipitate a clean product. And there are smart solutions to this, but that's a difficulty that comes with the hydrolysis. So, announced industrializations. This has a very high European focus, I should admit. But we have planned capacities here in 2025 by Syre. They're now building in North Carolina, though, in the US. We have had other planned industrializations, 2025 by Carbios and also by Eastman. Unfortunately, both of these have been postponed. Carbios didn't get enough funding, and Eastman is waiting for EU to get a more strong decision on the actual need to utilize recycled feedstock. Then we also have other announced industrializations by Gree, GRGN, Loop, Depoly, Garbo, and Cure. What should be mentioned here is that this is actually happening already now in Asia at quite large scale. So there are several actors doing bottle to monomer, but there are also now actors starting to do textile to monomer. And I could mention Tianjin. So they are, I think, now at the production capacity of about 40 kilotons per year. And there is also, I spoke to a Chinese colleague just the other day who's supervising what's going on in China. And I don't remember the name of the company now, but he said that it was just announced a 100 kiloton glycolysis process industrialized in China now. So we see that they're far ahead when it comes to scale. So what's the cost then of a chemically recycled filament yarn? So this data comes partially from a seminar held from Petcore. So of course, the chemical recycling has several different cost elements. So you need to have collection and sorting of your textile. You need typically to prepare your feedstock. That could mean removing hard parts, decolorization, etc. You have a section here from depolymerization and purification. And then the smallest share is getting back new PET polymer and then spinning that. And of course, each of these comes with a cost. For virgin PET, well, this price point changes all the time. Probably some of you have more recent data than I do, but we're at about half the estimated cost of chemically recycled PET. And when I spoke this summer to Tianjin, they said that this was approximately correct. So they were about twice the price of virgin material. I also spoke to another contact who had been on a business trip to China visiting some of these factors, and she said that on monomer level it was plus 80, plus 90%, but on yarn level plus 60 approximately on the price. And I'm sure that some of you actually have more relevant data there than I do. But what we see here is that chemically recycled comes at a premium, just as the mechanically recycled material that we used to from bottles. And you also see here that you have a lot of components here that you need to sort out in order to have a process doing the chemical recycling. Something else that might be of interest are, of course, the reported greenhouse gas emissions. Virgin PET, I took this data from Carbon Fact, so about 3 kilograms carbon dioxide equivalent per kilogram of PET. Our PET from bottles, about a third of that. Chemical recycling has a quite large spread. Depending on how you design your processes, you can come out with a much lower carbon footprint, but also actually a lot higher. Then, of course, a process that comes out at much higher carbon footprint probably would have difficulties industrializing. But it is perfectly possible to, if you aim to recover any byproduct, any additive, etc., that you might build a process that actually doesn't have a positive carbon footprint. We have developed a glycolysis process at RISE. This is basically a scale up from a lab scale process. There we see that we are at about 75% of the carbon footprint of then virgin PET. Cure, another glycolysis actor, is reporting a lot lower values. Syra is a little bit vague. They say that they can have up to 85% reduction. Redo, also glycolysis, and Carbios is doing enzymatic. They're saying that they will have about 50% reduction. But it should be mentioned here that LCA data is rarely accessible for these different actors, and that you should also take some caution when you compare LCA data from different actors, because depending on how you set your boundaries, you can end up with quite different results. And there I would like to give the floor to Anders from Rewind.
Yes, thank you very much, Anna, both for the introduction and for the possibility to present here today. So I'm going to talk a little bit about polyester recycling in general and the challenges that we see today, and then go into what we are doing at Rewind and how we are trying to face these challenges that exist. So I would actually like to start to elaborate a little bit more on the LCA data that you, Anna, showed us just before. And there have been a lot of reports available saying either that chemical recycling or textile recycling is favorable, or that it's just as bad as virgin textile production. And of course, all of those are correct. It depends how you look at it and how you are performing the recycling. So coming back to what Anna said in the beginning of the presentation, if you can do mechanical recycling, that is the obvious choice. It has the lowest impact and it's cost effective, and good from many perspective, but when it comes to textile, it's rather limited amount of textiles that are actually reasonable or doable to do mechanical recycling due to the complex blends, mixtures, colors, etc. And also because you want to get back the virgin quality, not downcycling. So that leaves you kind of with the chemical recycling, and comparing the main technologies, enzymatic hydrolysis, methanolysis, and glycolysis, show you that if you choose methanolysis or enzymatic hydrolysis, you end up almost in the same region as the virgin fiber production. So yes, you take care of the waste problem, but you don't really address the global warming problem, the carbon dioxide emission. However, glycolysis shows much better potential in that respect, and that is one of the reasons why we at Rewind work with glycolysis. So what do we work with? What is our feedstock? Well, for some time we have had the intention and clear aim to work with these post-consumer textiles that are separately collected since January this year. But what we have seen recently is that our aim or our thought that this would be accessible was not really correct. Instead, we have seen what some actors call a chaos in the collecting system. We see that second-hand and charity organizations have difficulties, and we don't see a establishment of a material sorting industry. This means that polyester recycling based on this separate collected post-consumer textiles is probably a little bit ahead of us in the future. Instead, we have started working with other fractions that we believe are more available in the near future. One is post-industrial waste, like clips and spills from the production. Then we are not talking about Northern Europe because we don't really have a textile industry at scale here. Instead, we are mainly talking about Asia, where that could be relevant. But one other interesting fraction and that really exists here is post-sorted municipal solid waste. So if you don't throw the waste textiles in a separate collecting, then you throw it in the residual waste. And the waste incinerators in Europe are under hard pressure to reduce the greenhouse gas emissions. So if you want to reduce the CO2 emission, either you can implement a carbon capture or you can start sorting out recyclable material, mainly plastics, prior to the incineration. And if you do so, you get different fractions of plastics. One can contain a mixture of polyester textiles and PET packaging. What is the challenge here is that this is a very contaminated fraction, so you can't do mechanical recycling, and it's a mixture of different kind, multi-layer packaging and textile with other content, and it's wet and moldy, but it works perfect when it comes to chemical recycling. So, but Rewin, what are we doing? Well, we are working with these three different fractions, and we have set up a process that is very much simplified on this picture. But what we do that differentiates us from all of our competitors is that we have totally skipped one of the major process steps that usually is here in the beginning of the recycling process, and that is the pre-processing. Instead of shredding, hard part removal, trim removal, compactation, agglomeration, pelletation. We take the textiles as they are directly into a chemical reactor where we dissolve the polyester. And by doing so, we increase our yield significantly and lower the cost of the process. The report that Anna referred to earlier state that all this pre-processing typically costs like 700 euros per ton of textile waste, and we have removed that with our pre-treatment reactor in our process. We also have a special type of catalyst that not only degrade the polyester into monomer, but also enable us to very efficient do decolorization. So our product is the BHET monomer that is completely white and that has a quality that it can be replace the virgin material, the fossil material in the big polyester producing plants in Asia. So our quality is proven. We have several polyester producers that have confirmed that our quality is as high or sometimes even higher than the virgin raw material that they use today. So that is not an issue. The processing is not an issue since we have cut off all these pre-processing step. What is more of a challenge is to accessing the feedstock for this kind of plant. As I said, we have hoped for this post-consumer collecting system, and we see that that is probably a few years ahead of us. But we are continuously working with all of these three options: the post-sorted municipal solid waste when it comes to a European or North European context, and also the industrial spill when it comes to a more Asian context. Right now, we are 3 weeks from factory acceptance test for our pilot plant. This pilot plant will be commissioned by the end of this year. And by having that in place, we will be able to produce hundreds of kilos for test batches sent to the polyester producers, so that they can do pilot polymerization and pilot spinning and confirm offtake of this product. And in parallel, we are working on securing feedstocks for our first plants. So with that said, I will stop and thank you for your time and hand over the word to Mega.
Actually, I would like to slip in between. Thank you so much, Anders. It was great to hear about Rewin and what you're currently doing and what you have planned ahead. One thing that I would like to remind everyone about is that the chat is open. So if you have questions to Anders, Mega, or me, then please type them in the chat and start already, and we'll have a bit of a question session at the end. So I will just do a short introduction to what is called all polyester solutions. And the idea here is to take complex products. It could be something like shoes, blinds, or car interior parts, as you will hear more about by the next speaker. And typically these would be composed of many different types of polymers and or other components, glues, etc. And these are represented here by these different colors. And the idea by doing these all polyester solutions is not that you could make everything into PET, because PET doesn't have the correct properties if you would like, for example, a glue. But to simplify and make everything into polyester-based materials. So the idea here is that some materials here are now the same, and some have been changed to polyester type materials. And you can see here that PET is based out of two monomers, so it's the terephthalic acid and the ethylene glycol, and they are repeated, so AB, 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 AB. If we have other types of polyesters or copolymers based on PET, this is a very schematic view, but you can see here that here we have actually a C included in the mix, and even a, even a D over here. So you can see that we now are adding more building blocks, but we're still keeping at least one of the original building blocks that we can then still try to recover in a chemical recycling process. And what we have learned at RISE, because we've been doing this for a bit, so we have tried then these different types of recycling methods. So methanolysis, hydrolysis, glycolysis. And what we have learned is that typically hydrolysis and methanolysis has a higher tolerance. So you get a higher yield of the monomer, of the terephthalic monomer, if you use hydrolysis and methanolysis compared to glycolysis for this kind of more complex polyester-based materials. And we have done both trials of full components or individual materials, and we do evaluation of both crystallized monomers or monomers in solution. And I also wanted to take the possibility to announce a new service that we have formalized, which is focusing on just this recyclability evaluation of polyester-based materials. So we do this on both individual components and finalized products. So if this is something that would be of interest of you, then please reach out to me. And of course, we also do consulting on what kind of materials could you use in such polyester-based solutions. But now, finally, I will leave the word to Mega.
Okay, thanks, Anna. Thanks, Anders. Good morning, good afternoon, or good evening, wherever you are. Let's talk about what we as a company from Autoneum think about the polyester and what do we see in which areas we are already using it. Just an introduction about Autoneum, because I think there are many people from Sweden may not be aware about Autoneum. We are an automotive tier 1 supplier company. It's a Swiss company based in Winterthur in Switzerland, and we are stock listed in the Swiss Stock Exchange. We are global mid-sized company with 16,500 people worldwide, with a 25 operating in the 25 countries, having a 77 production facilities which actually produce components and deliver to our customers, which are the OEMs. Just a quick review on 2024. We opened a research and technology center in China. We have an internal level up corporate strategy program to improve the several things. And we have a sustainable polyester-based product portfolio for the commercial vehicles, which we launched, and a fully recyclable trunk side trim made up of 100% polyester, again, was launched in last year. When we move forward in terms of financial, to give a quick update, we are 2.3 billion Swiss francs. That's our turnover, with a 5.3% EBIT. And if you look at the revenue, we are based on 4 different business groups: Europe, North America, Asia, and SAMEA. And on the right-hand side, you could see the revenues by customer. It's a chart which basically tells that we are having a very good diversification. And it's a good for a company like us, because we are not dependent on one specific customer or region. Where are we present? As you could see, we are present everywhere. In Europe, stronger, in North America, in South America, Middle East, and Africa. Particularly, I would like to highlight the blue names here in Asia, which we took over last year, and we own the majority share, and we are at the moment, and then in the future, it is a possibility to own it fully. The most core manufacturers we supply, some of them, or some of the brands, is listed here. Of course, you see also from Sweden, Volvo, and also the other companies, the growing new car companies from Asia. Okay, that was the introduction about Autoneum. Now let's get into the topic about circularity. So I think this is a very nice picture which talks about the circularity in the automotive sector. Basically, the circle starts from this point where you have been awarded a business from a customer, and the product design, everything, the whole development process kicks in, and it takes around 18 months. Sometimes it's shorter, sometimes it's longer, depending upon the customer, depending upon the product, but it's in an average we are talking about. This is the time from the award to develop the product and bring into the serial production. Then you have the serial production, and from the serial production, it goes into the car, to the car manufacturer. That happens in a very few weeks. We all have the just-in-time concept, and our automotive is a very lean. So basically, once you have a value-added product, it directly goes into the customer, and the customer builds in, and basically it goes out from the customer's place. In this case, it's OEM. From there, the cycle is much longer. We are talking about a part inside a car, particularly when we talk about the floor system inside the car. And then we are talking about basically 15 years, or in some cases, even 20 years. So then once it is going to the end of life, then if we could take the part, and then it's again, we are talking a very short turnover, few weeks, then you could basically reprocess that material and bring it back. So as you could expect, it's not like in the bottle industry, or it's not like in other industries where the life cycle is much shorter, but in automotive, the life cycle is much, much longer. So we need to have a basically thinking or a design thinking right from the beginning. When we talk today, the end of life might be happening after 20 years, but we should design the product today in a specific way so that we could recycle it and make use of this material after 20 years. Of course, there is a very short gain immediately during the part production. There are trim waste which could occur. I will come to that point later, which could be reused immediately. But the real gain or the end of life will happen longer. But the design thinking has to be immediately there in order to realize that later. So we as a company strategically looking polyester as a kind of an monomaterial solution for several reasons. There are a few of them which I have highlighted here. The first one is it's available in different format properties. You can fine tune and you can get it either in flakes or in other sort of materials. It is suitable for interior and exterior pots. That's where Autoneum is actually specialized. We are an acoustically core competence with acoustic and thermal management, and we supply the interior and exterior pots to our customers. And there is a good availability of a post-consumer waste thanks to globally available mass production and a lot of industries in the polyester. There is a good availability of that one. And then final point is that it's one of the polymer which has got a low greenhouse gas emission compared to others. So the components that we can make out of this material could have potentially can have a high recycled content thanks to already available the post-consumer and the post-industrial waste. And then we have a full recovery and recyclability at the end of the vehicle life cycle if you make everything in the polyester. And it's more energy and cost efficient recycling process when you compare to other processes, depending upon the process, whether you are talking a thermal process or a chemical recycling. In our case, we are talking about a thermal process, which is taking out and melting and making it a new fiber or yarn. This is a kind of an interior view of a car where you could see different parts inside the car and maybe on the outside underbody. And these are all the 4 product lines basically where Autoneum is very much active. So we define the monomaterial means it's made from a single type of material throughout, which can be thermomechanically recycled. As I mentioned before, you take the polymer, you heat it, you melt it, and it could be passing through an extrusion and or to another process, and you get out a value added, not a cheap product, a value added product. Without the need for separation or disassembly and without significant loss of value. So that's exactly how we define the monomaterial. And if you look at here are the 4 product portfolios, the interior floor, trunk and interior trim, engine bay or underbody. The textile materials we are talking about is 20 kilos in terms of the interior floor, and 4 kilos in terms of the trunk and interior trim, and 3.5 kilos on the engine bay, and 7.5 kilos on the underbody panel. And in that 4 product lines, if you look at each one, you have basically up to 80% of average recycled content on the portfolio, depending on the product line. And it's up to the 18% of the total plastic if you bring it back, and up to 65% of CO2 reduction, and excluding the usage phase, because we know the usage phase depends on the weight and other things. And then up to 35% weight reduction we can bring in by having this material in terms of the monomaterial textile composition. For us today, we just quickly see the interior floor. That is where I'm coming from. Here, this sounds to be a little bit a complex slide, but it's much easier. On the left-hand side, you see a traditional carpet system, floor system, how it would actually look like. You have several layers and several polymers. That is the main drawback today when we think about, do we want to recycle this material after 20 years, or the today from the trim waste, we cannot do it because the top layer of a different polymer, the individual layers are different polymers, and it is a mix of thermoset, thermoplastic, and a kind of a polyurethane system, so which makes it extremely complex, and they are landfilled, and there is no end-of-life concept. However, this was been the traditional. We as a company been working in this last 4 or 5 years, and then we came up with a simplified bill of material monomaterial carpet system, where we made, as per our definition in the previous slide, all the polymers or all the layers are of the monomaterial polyester polymer. And by this, we could actually also bring a 50% recycled content. We could bring trim waste, which is generating during the molding process. We could recycle it 100%. And then the end of life, it is a system you can take it out after 20 years and it could be completely recycled. So I think this is something a very big and bold step. It sounds to be very simple, but you need to still fulfill all those performances, what you have got here, without going in the quality level lower. And the bottom you see, when you take the original carpet as a kind of a baseline, as 100%, and then you basically, how the stepwise you could reduce it, when you have the monomaterial system, basically, we have the recycled cotton, which could be cheaper, but you can only do the 50% reduction here. Then you can have the mechanical recycle. It's not the value added. Basically, you chop and you use it in another area in a little bit of a downcycling. But then you have the thermomechanical recycle, which we have in a 75% advantage, basically. Going there. And then the next one, in terms of the different kind of products within the carpet, we have a segmented, a premium, needle punch, mid-low segment, SUV. So we are trying to address all the market groups. Here you could see what I was talking about, the combination of the recycling and the acoustic competence. When you have the trim waste, we could basically have this post-industrial recycling loop, which is a 30%, which is basically coming from our production waste, and we can take it back and use it again in a value-added product. And then the longer cycle, which is talking about 10, 20 years, which is the post-consumer end-of-life recycling after the usage phase. And we assume here we could still get a 35% of an material coming out of this loop. So then combining, we could achieve a 65% of a 65% of raw materials that could be potentially used in the future products in ours, so that we are less dependent on the virgin or the fossil-based materials going forward. So the key takeaways are basically our vision is actually to have a zero waste through a sustainable design. That would be fantastic if wherever we could reduce the waste, if possible. And there are, but areas where we cannot completely do today due to the shape, due to the geometry, and due to the products which we are in. Which we cannot do that, then we are shifting towards the monomaterial components, which is a very key to the circularity. So that's the second step where we cannot do that one. Then the third one is actually the autonomous interior products, which actually enables to meet the latest end-of-life regulation, because there is a regulation which is coming. We should take and we should reuse this end-of-life materials back into the car. So the today wastes are the materials for tomorrow, because once we have this monomaterial and once we have the waste collection system established from the end-of-life vehicle recycling, and the waste becomes a very important raw material for the tomorrow, and also to have the effective cost effectiveness. So all we need to do is to act together as from our sub-suppliers, from our customers, together to design the product in such a way that we meet this end-of-life targets in 2032. And we are also first company to go in the product with a 100% monomaterial flow system into the market, and so that's we are already start supplying to our customers, and we expect the other customers are also following it very closely, this one, and very rapidly to fulfill this target of this end of life target in 2022, and this makes a kind of a less dependency on the oil and fossil, and makes our waste to use more effectively and efficiently. Yeah. So thank you very much for your attention.
Thanks a lot, Megan, and thanks a lot for these hands-on tips that came here on this last slide. It was really excellent. I'd like to mention again that there is still some time to ask questions in the chat. Please go ahead and do that. We'll very shortly have our Q&A section. But actually at RISE, we tried to do a bit similar to what Mega did and formulate some tips. So how could you what could be your starting point here? And of course, these starting points are very different if you're a material producer, if you're a researcher, if you're an OEM. So we tried to have some tips maybe for everyone. And as I mentioned in the beginning, I think this is about finding your angle. So if we can agree that our joint direction here is to try to reduce the carbon footprint of the products that we're having, then we can do that in many different ways. And one of these ways could be to design your products for recycling. I'm a little bit bold here to say use RISE framework tool to guide you. You will be able to do that, but it won't be released in another 2 months. So you'll need to wait a little bit in order to get that kind of guidance. And please make sure to follow us on Textile@RISE on LinkedIn, and then you will not miss the launch. Another tip, of course, is to boost the recycling actor. Either you invest, if you have a lot of money, or you sign up to buy recycled feedstock. Of course, that's a security that allows these startup companies to be able to go ahead and invest in larger industrializations. Tip 3, change the renewable energy in the production process. So we can target this in many ways. You can use recycled feedstock, but you could also think about what's the production process of my materials today? Can I push my producers or help my producers to change to renewable energy? And another one in the same area is to request milder wet processing or switch to completely new methods for dyeing and finishing. One thing that actually is quite compatible with chemical recycling is dope dyeing, so that you dye in the melt rather than the traditional exhaust dyeing typically used for polyester. So that's also something that could be of use. But then let's go to questions. So the first one I see here is from Magda, and I think we could direct it to both Mega and Anders. So the question is, do you see a need for any policy changes in Sweden or the EU to make recycling more profitable or large scale? Maybe we could start with Anders.
Yes. So from my perspective, I think that recycling can be profitable and could work at large scale without any direct policies regarding the recycling itself. But what's our issue is the securing the feedstock. So I think that we need to look at how other countries have done or other sectors. For example, in plastic packaging, we have a already established EPR scheme, and that means that the collection and the sorting, the cost for that is covered, and that have enabled plastic recycle to grow during the past few years. And we see kind of the same in some countries like France, for example, where they have had this EPR scheme for waste textile for some 10 years now, that they can build and scale up textile sorting prior to recycling capacity coming in place. And we need to have the textile recycling in place, or the textile sorting in place, before we can build textile recycling. Otherwise we have nothing to work with. So EPR schemes that can cover the collection and sorting, I think that is a key moving forward. Otherwise we will not succeed.
Thank you very much, Anders. So, Mega, do you have any input on needs of policy changes?
Well, I'm not an expert on the policies and so on, but what I think is the awareness. The awareness of having the recycled material and its importance in every component. And we should always ask this question: how can we help our customers to fulfill their goals, which they are always having on their top list, and also make aware to the people that recycling can be higher quality. It is not, there is a belief system long rooted that recycling was not seen, but today the technologies and the quality what we have, it could be of a same quality, or even at some areas or some products could be of better quality. Having this awareness, I think, and spreading this awareness is a very good.
Thank you very much. We have a question from Panagiotis to Anders. Since you mentioned that you can also take blends, which are the type of blends that can be accepted in your process? And how do you process the other components of the blends that are not polyester?
Yes, so that is a very good question, and it depends on what type of feedstock we are working with. So normally we have these post-consumer textiles that contains mainly polyester. Then we have some cellulosic, like cotton and other man-made cellulosic fibers. There is elastan, there is a little bit of nylon, there is a little bit of wool. Of course, there is hard parts, there is contamination like dirt. Perhaps there is mold as well on the textile. That is not an issue from the recycling perspective, but the residual is a mixture of what we do not recover, and perhaps pretty hard to do anything useful with. Then we have the post-industry alternative, where we have very well-defined feedstock. For example, it could be a polyester cotton blend, and then we get a cotton out of that can be mechanically recycled. The same goes with if we have, like from car interior, we have this polyester polyurethanes foam mixtures. Then we can extract the polyester and recover the polyurethane foam for chemical recycling. So it's very much dependent on what type of feedstock. So sometimes you can recover what's left, but then it needs to be well defined. In normal waste, what is not polyester can't be recovered, not currently at least.
Thank you. A question to Mega from Urban. How come the raw material CO2 equivalent is higher, but the conversion and semi-finish lower on the thermomechanically recycled PET product?
Okay, I think actually this is from our sustainable team, which they have put together. But my understanding is, for the thermomechanical recycled polyester, you're not going for the fossil source, you're taking the material which are already from the recycled source, right? So the process what you involved is basically making the fiber. That is similar to like making any fiber of the virgin fiber. So that explains why the raw material is completely, the one before the polyester production, everything is completely cut out. The only energy involved is basically recycling it and making it to the fiber, right? That could explain the lower raw material CO2 equivalent for the comparison to the virgin or the other carpets. The other factor which we see here is the remaining process. What you mentioned about the conversion process, and other one, it probably should be the same. I will check why it has got a little bit lower value than the other. I will come back to you on that one.
Thank you, Mega. I have a question here on how do recyclers such as Rewin see the opportunity to collaborate with companies or brands on take-back programs? And then especially since as you mentioned, Anders, you feel like the collection is not working very well at the moment.
Yes, that is of course very interesting, but one should know that chemical recycling requires very large scale. Take-back programs could be a add-on to the feedstock, but not the entire flow, I think, because what we are talking about is a scale from 20,000 ton up to 50,000 ton annually for building a plant. And then I don't think that take-back can fully cover that volume that is required. But of course, as a top-up, definitely.
Thank you.
Anna,
yeah, please, Mega.
Okay, I just, sorry, I was just looked at the question again, I read it again. So the reason is polyester carpet is also lighter, so there is a weight involved. So we are not talking about why the conversion values are lower, it's because the weight. So that could answer the question of Urban.
Great, thank you for that clarification. I think we have another question that's quite important to take, and that is that the RISE and the Rewin reports have quite different emission figures, for example, in the case of enzymatic recycling. Could you clarify this? And what are the key differences in their underlying assumptions? And so from my side, I took reported data from Carbios, who is a recycler or doing enzymatic recycling. And then, so, and as I mentioned, so LCA data is typically a little bit difficult to compare. Maybe you would like to comment on this as well, Anders.
Yes, so just to take one example, when you do your LCA, then you need to, what type of energy are you going to use in the factory? Will it be renewable energy? Then you will get one outcome. And in the other end, you can use a coal-fired plant to produce your electricity and your heat. And then you will get a completely different number for the LCA. So you should be very careful comparing this kind of data, especially if you haven't done the LCA by yourself or in the same manner. And I actually think that this claim by Syre is rather good, up to 85%, because if you consider like renewable energy and the best case, then it's perhaps 85%. But if you consider a localization where you have fossil energy and not the right integration possibilities, then it will be much lower, and that goes for all of the processes.
Thanks a lot. I see that there's still room for a lot of more discussion, but unfortunately we're running out of time. I see that some people have already left the meeting, but I'm sure if you have specific questions to either me, Anders or Mega, we would be super happy to take your questions by email afterwards if you feel like you did not get the response that you were asking for. So thank you very much, Anders and Mega, for joining RISE in the seminar. And thank you everyone who has been listening in. I hope that you've learned something. And I hope to see you again soon.